Hello everyone. In this lecture I'm going to explain you how to solve homogeneous and Bernoulli equations. We're going to start with homogeneous equations. Equation is called homogeneous if the function on the right side can be represented as certain form. So normally we have first order equation looking like this. It's not linear equation or not necessarily linear equation. Y prime equals f of xy. If you can represent this right side function f of xy as f of y over x, f of the ratio between y and x, equation of this type is called homogeneous. Example. We're going to start with example. Example number 1. dy dx first derivative equals y minus x over x. Typical homogeneous equation. Why? Well, I'm going to start working with function f. I'm going to divide both numerator and denominator by y here and by y here. Oh, by x here, sorry. By x here and by x here. So the first term is going to be y over x. The second term, x over x, is going to give me 1. And the last term is going to be x over x, is going to give me 1, 2. So I'm going to get y over x minus 1. You see that my function now depends on the ratio of y over x, which is turning my equation into homogeneous. What is the method of solving of homogeneous equation? Method. We are going to use substitution. And substitution is going to be next. V of x equals y of x over x. So we are going to call this ratio my new variable v. That's going to be v. What is going to happen to the derivative? Well, let's look at our equation for v. What is going to be y from this equation? Y of x from this equation is going to be v of x multiplied by x. If I want to find derivative of y by dx, y prime, I'll need to differentiate this product v and x by dx, right? Because it's a product, I'm differentiating it using a product rule. I differentiate v first and then get v prime. I don't know v, so I'm just going to keep it as v prime. Copy my second term. Plus, I'll keep v and differentiate x. It's going to give me 1. So my derivative is actually v prime x plus v. Well, good idea to remember this expression is going to be repeated through all homogeneous equations. Now I'm going to substitute everything into my equation back. So instead of the derivative, I'm going to put v prime x v. So v prime x plus v. Well, here I already kind of did substitution, right? It's v minus 1. And I can simplify a little bit this equation by subtracting v from left and right side and get v prime x equals negative 1. Not a very complicated equation, actually can be easily solved by separation of variable, right? dv dx multiplied by x equals negative 1, from where dv equals minus 1 dx over x. I'm moving this part to the right side. Well, integral of both sides is going to give me v over here, and on this side it's going to give me minus ln of x, right? Well, minus is going to stay, this is ln, and plus a constant. Well, it's not the final answer yet, right? Why? Because actually I was doing substitution, so that's not my y. I'm searching for y. V is a substitution. I'll need to find y using back equation for substitution. So I'm going to write down that instead of v, I'm going to write down that it's y over x. So y over x equals minus ln of absolute value of x plus a constant. To find y, I'm just going to multiply everything by x. So y equals x constant minus ln of x. Well, can we simplify it a little bit? Yeah, guys, we can simplify it, but I'm not going to do it. You can bring constant inside of ln because you know that constant, any arbitrary constant, can be ln of any arbitrary constant, positive. Because, well, ln changes from negative infinity to positive infinity, so if you put arbitrary number under ln, it's going to return you arbitrary number, not the same, but still arbitrary, so you can combine these two together. But it's not going to simplify my answer a lot, so I'm not going to do it, okay? I'm just going to move to example number 2. Okay, example number 2. dy dx equals 3y squared minus x squared divided over 3xy. Let's first check if this equation is homogeneous. So I'm going to divide my right side in numerator and denominator by x squared. Why by x squared? Well, because I have y squared, right? To get y over x, I'll need to make it y over x squared, actually. So what I have in numerator, y squared over x squared. So I'm going to write down y over x squared. X squared over x squared is 1. In denominator, one of the x's, this x cancels with one of this, right? But another one is going to stay, so it's 3y over x. Well, we see that my function can be represented as a function of the ratio y over x. So we are going to get homogeneous equation and we are going to use a substitution. V, again, equals y over x. Guys, I don't want to do the differentiation one more time. I'm just going to copy the ready result, okay? So y prime, but you know, it's not difficult to get y prime. If you forget the formula, it's not difficult to get y prime, right? Remember that to do a full substitution, you will need to get this one. This is v. This is also v. That's v squared and just v. But here you will need to know what is y prime. And to do this, you will need to kind of calculate it. I'm going, because I did calculate it once, I'm just going to use a ready formula. So it's v prime by x plus v. But if you forget, just remember, multiply back by x, differentiate as a product. Now I'm going to plug everything into my equation and see what I'm going to get. So I have v prime multiplied by x plus v. I'm doing it instead of the derivative, right? And on my right side, I already have 3v squared minus 1 over 3v. What I think I'm going to do, I'm going to simplify this equation by moving this v to the right side. So I have v prime x equals 3v squared minus 1 over 3v minus, well, if I take this v and multiply by 3v and divide by 3v to bring it to common denominator, you see what I'm going to have? I'm going to have v squared multiplied by 3 with minus, which I have over here exactly. So what I'm going to get is just negative 1 over 3v. Well, this is also separable equation, right? I'm going to move v on one side and x on another side. So I have dv over dx multiplied by x equals negative 1 over 3v. From where moving this v to the left side and this dx and x to the right side and this one is to the left side, I'm going to get v dv, right? It's a numerator, and I'm going to have minus 1 over 3 dx over x. Now I'm going to integrate left and right side of this equation. And I think I'm just going to write down my answer over here. So it's v squared over 2, right? Integrating this part, equals negative 1 over 3 ln of x plus a constant. Now that's not my final answer because my v is not a variable. Actually, my variable is y. So what I'm going to do, guys, first I'm going to multiply everything by 2. And then I'm going to substitute instead of v squared, my substitution, instead of v, y over x. So I'm going to write down y over x squared here. I'm going to move this 2 on this side. So I'm going to get minus 2 over 3 ln of absolute value of x plus 2 constants. The last step I'll need to do is to multiply everything by x squared to kind of get rid of x on this side. It's not gonna solve it for y, but it's going to get me closer to the final answer. So y squared equals x squared multiplying by x squared here is going to cancel this x squared. Can we still see it? Maybe not, right? I'll need to move it a little bit. So minus 2 over 3 ln of absolute value of x plus 2 constants. Well, can we simplify this one? Yeah, guys. For example, instead of 2 constants, you just can invent a new constant here, and that's going to still be an arbitrary number, right? Second, if you wish, you can combine this constant together with ln by representing this as ln of a constant and bringing it together with x. It's not going to make your answer looking much nicer, but it's going to be a little bit shorter. I'm not going to do this just because I'm too lazy. But you can always do it. Should we extract a square root? Yes, if you wish, you can extract a square root of both sides, and then you are going to have absolute value of x here instead of x squared, right? And the square root of this expression. Well, I would suggest you to not extract the square root, because as soon as you extract the square root, you will need to put restrictions on what you're supposed to have as a constant, because actually you cannot have negative numbers under the square root. Here there are restrictions too, but they are kind of invisible. But if you extract the square root, you will need to say something about like the expression under the square root must be greater than 0 or equal. Okay, I'm going to leave my answer like this, and I think you can do it too. Okay, let's move to the next case. Move this page, set it again back on the top, and move to Bernoulli's equations. So number 2. What are Bernoulli equations? Well, Bernoulli equations are a first-order equation of a special type. On the right side, you are going to have a function y. I'm going to write down an example of Bernoulli's equation. Y prime p of t y equals g of t y to the power of n. Here, n is not equal to 0 and not equal to 1. Why do we have restrictions on this? When n equals to 0, we are just going to have 0 here, and y to the power of 0 is just 1, and we are just going to have the first order equation, which we solve normally by integrating factor, right? If it equals to 1, we are going to just have y here, right? If you have y here, you can combine with this y, and again, we are going to have even not integrating factor, but just separable equation. So cases when n equals 0 and 1 are not special cases. They are just solved by easier methods. Now, how do we solve this equation? Let me do some modifications of this equation so you probably will understand better why are we solving it this way and the new substitution. I'm going to divide the whole equation by y to the power of n. I'm going to get y prime over y to the power of n plus p of t y over y to the power of n equals g of t. How it's better? Well, it's not better yet. I'm going to simplify a little bit this expression and write it down like this. Y prime over y to the power of n plus p of t y. Well, guys, it's very easy to simplify this and write down what? That's 1 on the top, right? And this one sits on the bottom, so it's minus n equals g of t. Now I'm going to suggest substitution method. Substitution v equals y to the power of 1 minus n. So we actually are setting up this term equals to v. So what are we supposed to have over here if we call this v? Well, this, instead of y prime, we'll need to kind of find it out what it's going to be, right? What I'm going to do here, I'm not going to actually solve for y prime by extracting a root over here or doing like solving for y prime. I'm going to differentiate this expression. So I'm going to differentiate left side and right side. So I have v prime, if I differentiate this, right? What is derivative of this? Well, derivative of y, which depends on t actually, it's a composition, right? So it's 1 minus n, the power 1 y 1 minus n minus 1. We have to lower the power of the power function by 1 unit, right? And then we differentiate the inner function. Inner function here is y of t, so we differentiate y. Now I'm going to rewrite this expression a little bit different. I see that's 1 and minus 1. They both are going to cancel each other, and I'm going to put this y to the power of negative n in denominator. So I'm going to have 1 minus n y prime over y to the power of n. Now I'm going to compare this expression to what I have in the equation and see, wow, it's exactly the same thing, just without this coefficient. Well, what I can do, I can solve this equation for y prime over y to the power of n. I just can divide both sides. This one by 1 minus n and this one by 1 minus n. So it's v prime 1 minus n. And I converted totally the whole equation to v. So my equation now looks like this. V prime over 1 minus n plus p of t v equals g of t. Now you can recognize our normal equation which we solve with integrating factor, right? That's going to be the way to finish the problem. Let's consider example. Let's start with example. So example number 1, t square y prime plus 2ty minus y cube equals 0. This equation does not look like Bernoulli's equation, right? First, it doesn't have any right side. It has 0 over here. Second, you even don't know what is n over here, right? So what we are going to do, guys, we are going to start with moving the powers of y, which is this one, right, to the right side. So we're going to write down this equation as t squared y prime plus 2t y equals y cube. Okay, it looks a little bit better. I do have y cube here, so I'm probably going to assume that my n is equal to 3 as a Bernoulli's equation. Now, if I compare it to standard Bernoulli equation, I see that there is no coefficient in front of the first derivative, right? And I have t squared. Maybe I should get rid of this by dividing by t squared. That's what I'm going to do. So I divide the whole equation by t squared. If I divide by t squared over here, I'm going to get 2 over t y. And that's 1 over t squared y cubed. Now my equation looks exactly like Bernoulli's equation. Y prime, y prime. P is 2 over t, p of t, right? And g is 1 over t squared. And y is to the power of 3, so it's Bernoulli equation with n equals 3. What is going to be substitution according to my idea of substitution is going to be y to the power of 1 minus n. In our case, it's going to be y 1 minus 3, which is going to be y minus 2. So, well, in other words, it's 1 over y squared. That's going to be substitution. Well, let's see how it's going to help us. So, guys, I don't want to deal with y prime again. If we divide by, well, by what should we divide here? Well, we're supposed to divide by y cube, right? Maybe I'm going to do it once. Plus 2 over t, and y by y cube, it's 1 over y squared, and here 1 over t squared. Well, I already know that 1 over y squared is v, right? So this one is going to be v. I know that this one, according to my calculations before, is going to result into v prime 1 minus 3, which is going to give me minus 2, right? If you wish, you can always check it. Maybe I should check it once, right? So what is going to be v prime? V prime here is negative 2 over y cube. I'm differentiating this as a composition by y prime, right? Because y here depends on t or on x, whatever is variable. Here is t, right? Well, I do see y prime over y cube, so I just need to move this negative 2 in denominator here, and that's going to give me substitution v prime minus 2 plus 2 over t v equals 1 over t squared. Good. We moved our equation to the first order linear equation, which we do know how to solve. What I'm going to do next? Well, I'm going to multiply by minus 2 the whole equation. So I'm going to get v prime plus, minus 2 2v over t. And here I'm just going to write down minus 2 over t squared. Well, this, if I multiply this, I'm going to just get minus 4, right? That's minus 4. I'm going to try to find integrating factor here. So I'm going to use integrating factor mu, right? If you still remember, integrating factor mu, it's a function by which you multiply the whole equation. So we are going to have mu v prime plus negative 4 over t v mu. I'm going to put it in parentheses. And minus 2 over t square mu, right? This one, it's like part of the derivative mu v prime, and this one is supposed to be v mu prime. Well, we do have v here, so this part is going to combine to mu prime, which is going to give us equation for mu prime. Mu prime equals minus 4 over t mu. Not difficult to solve. Separable equation, right? Instead of mu prime, d mu over mu. Here minus 4 over t dt, which is going to give us what? Ln of mu minus 4 ln of t. There is a constant, but remember that we care only about one solution here. So I'm going to write down raise e to the power of this and e to the power of this. I'm going to get mu, and I'm going to get e to the power of ln of t to the power of minus 4. This is going to cancel and give me t to the power of minus 4. I'm going to skip absolute value. I'm going to just consider positive t's, because minus 4, it's the fourth power actually in denominator, right? Okay, good. So this is my integrating factor. If I apply integrating factor here, it's supposed to roll into integrating factor v, right? Integrating factor v. My integrating factor is, I'm going to write down mu v. Derivative is going to be equal t to the negative 4 by v. Derivative equals minus 2 over t square. And this integrating factor is 1 over t to the negative 4. Double check. Oh, why did I put it in denominator? It's supposed to be multiplied by t to the negative 4 multiplied. I was thinking like negative 4, put it in denominator, but actually if it's negative 4, it's supposed to be numerator. Okay, so what I have over here, I'm integrating both sides. So I'm integrating t to the negative 4v prime dt. And I'm integrating this expression too. Well, I'm going to write it down as minus. I'm going to put this negative 4 in denominator and have 2 over t to the power of 6 dt. A bit confusing, but let me write it down here. It's 1 over t to the power of 4. So basically my integrating factor is 1 over t to the power of 4. If I multiply it by 2 over t to the power of 2, I'm going to get power of 6. Here integral and derivative are going to kind of cancel each other. V, that's minus 4. Here I'm going to get, if total power is 6, so I'm going to get 2 over 5 t to the power of 5 plus a constant. If I differentiate this, I'm going to get 5 here, which cancels with this, minus, and t to the power of 6, which is kind of correct answer. Now I'm going to move this t to the power of 4 to the right side, multiplying by it. So my v equals 2, 5t to the power of 5 plus a constant, multiplied by t to the power of 4, right? I mean, if I multiply by t to the power of 4 both sides, I'm going to cancel this one, and I'm going to move it over here. I don't want to rewrite everything. I'm just going to simplify it a little bit. So I have 2 over 5t plus constant t to the power of 4. Well, it's not the final answer yet, right? Because we're still searching for y. Well, I think I'm going to maybe put one more line here. I don't know if you still can see. Yeah, I still can see it. And then move to the next page. So my v is what actually? My v is, let me go back. It's 1 over y square. It's 1 over y square. So what I have here is 1 over y square equals 2 over 5t plus ct to the power of 4. I should go back and find what is going to be my y, right? Well, basically here, guys, maybe you can stop at this point, because you can flip over this expression and this expression and get something like this. So y squared equals 1 over 2 over 5t plus c t to the power of 4, but I don't think that it's going to make a big difference actually, like keep it this way or keep it this way. Normally, guys, if you have initial conditions, you can find c and then maybe it's gonna simplify better, but otherwise that's the final answer actually, and you can keep it like this or you can keep it like this. Okay, now guys, I did consider one example myself. I want you to try another example by yourself. Remove the page, set it up over here at the top, and ask you to solve something on your own. So try to solve by yourself next problem. Y prime equals 2y minus 3y squared. If you see powers of y, most likely it's going to be Bernoulli's equation. So what you can do, you can stop my video and try to solve the problem. And I'm going to count to 3 and provide you with solutions so you can kind of compare your final answer with my solution. Okay, so 1, 2, 3, and you can turn on the video again. Solution. So here I deal with Bernoulli's equation, y prime minus 2y equals minus 3y squared, right? Bernoulli equation has order 2. And my substitution v is going to be y 1 minus 2, which is 1 over y, right? Minus first power. Well, I'm going to do the steps. I'm going to do division. So I'm going to divide by y squared here. So it's y prime over y squared minus 2 over y equals minus 3. Well, this is almost my substitution, right? If it was 1 over y, it would be just v, but 2 over y, it's 2v, right? For this one, well, I don't know, maybe I should do differentiation. So y prime equals minus 1 over y squared, y prime. Well, you see that that's exactly the expression we have over here, just without minus. So you can write down that's minus y prime minus 2v, minus v prime, sorry, equals minus 3. And maybe put all the pluses and have v prime plus 2v equals 3. What I'm thinking is I'm going to solve this as separable equation. So I'm going to move 2v over this side, and I'm going to write down dv well, let's call variable c equals 3 minus 2v. So dv over 3 minus 2v, I'm moving this one over here, equals dt. From where? Well, guys, what is this? That's actually a ln of 3 minus 2v. If you differentiate this expression, you are going to have extra minus 2 in front, right? Just because it's going to be 1 over 3 minus 2v, and you differentiate minus 2v, you're going to get extra minus 2 in front. To not have it, we are going to divide by it. Equals t plus a constant. Okay? And you can try to simplify it before you kind of move to the final answer. So I'm going to multiply by negative 1/2 both, by negative 2 both sides. So I'm going to get just plain ln here. Negative 2t, negative 2c. Well, constant is an arbitrary constant, so I'm going to just label it as a new constant. So I'm going to write down minus 2t plus a constant c. Okay? Now, maybe not necessary step, but I'm going to put e to the power of both sides. So e to the power of ln 3 minus 2v equals e to the power of negative 2t plus a constant. Well, here maybe I'm going to kind of combine this constant and e and have a constant c to the power of negative 2t. Here, canceling this is going to give me 3 minus 2v c e to the power of negative 2t. Is it the final answer? No, we still need to look for y, right? So I'm going to put back, instead of v, 1 over y, which I had over here. So it's 3 minus 2 over y, absolute value, constant e to the power of negative 2t. Here, constant is positive. This constant is strictly positive. But if I remove absolute value, I can allow it to be negative, and that's what I'm going to do. So here I allow my constant to be negative. C can be positive or C can be negative. Last step, maybe I'm going to move this 2y on this side and it's constant on another side. So 2 over y, 3 minus c e to the power of negative 2t. Well, I'm very close to the end. Maybe I should flip everything over, but I want to see if 0 constant is a solution. Should I kind of allow my constant to be equal to 0? Well, yes, what is going to happen if my constant is equal to 0? So far it can be positive or negative just according to my solution, but if my constant is equal to 0, I'm going to have 0 here, right? If I have 0 here, I'm going to have 2 over y equals 3, or y is going to be equal 2 over 3. Is it going to work here if I substitute y equals 2 over 3? Is it going to be a solution? Well, let's check it. Maybe I should, like, c equals 0 is going to give me 2 over y equals 3, from where y equals 2 over 3. I'm going to plug it into my equation back. If it's a solution, I'm going to allow my constant to be equal to 0. If it's not, well, I'm not going to consider it. So let's check. Derivative of 2 over 3 is 0, right? 2 over 3 here minus 3, 2 over 3 squared. Well, what we see, have 2 squared, 3 cancels with one of these 3, and 3 stays here. So it checks. Actually, we can allow my constant to be equal to 0. So here constant can be any number, positive, negative, or 0, because 2 over 3 is fitting into the equation. Well, very good. Is y equals 0, which we are losing when we are doing division by y square, going to be a solution? Another question. Y equals 0. Is it a solution? Well, let's just, y equals 0 is a constant, right? If you plug it in here, you are going to get, 0 equals 0 minus 0. It's a solution. Solution 2. Okay. So it looks like we found all the solutions. So this is going to be the general formula, right? In this general formula, y equals 0 does not go, because if you put y equals 0 here, you're obviously going to divide by 0. So this formula does not include y equals 0. If you give solution as this formula, you have to add y equals 0 as a separate solution, okay? But what is good, that the constant here can be any number, positive, negative, or 0. Maybe I should write down the final. 2 over y equals 3 minus c to the power of negative 2t. So these two are making a solution. C, any real number. Okay, so we're done with Bernoulli's equations too. And next lecture we are going to do some special second order equations.